Okay, thank you. Thank you for the introduction again. And I personally also enjoy the other people's lecture a lot. And thank you very much for this nice, wonderful organization. So the last lecture will be mostly painful for you. Is this, unfortunately, this. So, so what I want to do today mainly is to sketch the construction of the Beilinson-Kato zeta element. So this is maybe the most painful part of this lecture series. Because it's quite complicated and involved. And yeah, although I would put spend lots of time, I mean, I will use most of the time of this talk to the construction, but still I can only give sketch. And I expect I can give no proof. And even, yeah, compatibility, there's no time to check. And of course, if you are only concerned, the application of Kato's Euler system, like this lecture might not be very helpful. But like if you are considering the construction of new Euler system, especially following the Raffler-Jervis program, then this kind of idea will be useful for you. So okay, let me remind my experience on Kato's Euler system. So when I first read the paper, I mainly focus on the applications. So I want to figure out what the element is the correct element I should deal with. And first I looked at the following element in Kato's paper. So which makes me like a very confused because of lots of notation. And F will be modular form. And M will denote like a Q zeta M, or its maximal piece of extension. And where all these other CD, RL prime, QCS, yeah, where do they come from? That's my question. And that's what we want to do today. And after having this, we can really construct the zeta elements we deal with in this lecture series. I just denote by like this, and there exists an explicit formula for this. So our main focus lies in here. In order to figure out the meaning of this notation, we need a geometry of modular curves and specific functions of that. That's would be kind of main objectives of this talk. So need geometry of modular curves and specific functions on them. And we will review the theory of modular forms and modular curves, but in an algebraic way. So, okay. So modular forms and modular curves. So n is the level will be larger than or equal to 3, and yn is the modular curve over q of level gamma n the full congruent subgroup without cusps. And this curve is represent the functor. So a functor from Q scheme to SAT. And the scheme S maps to the following triple. Indeed, its isomorphism classes of triple. So E, E1, E2 is E is an elliptic curve over S, and E1, E2 is a pair of sections of the elliptic curve E over S, and which form a Z mod NZ basis of n torsion of E up to isomorphism. Then what is known is the smooth irreducible affine curve. And also, one thing I want to remark is that its constant field is not Q, it's the Q adjoining nth root of unity. So the constant field of Yn is Q zeta n. Okay. And Xn will be a smooth compactification of this Yn. Okay. And Xn is a smooth compactification. And if we change the label, then there's a natural map. So if I put Yn times small n, and it surjects to Yn, then as a point, like it is triple maps to the same elliptic curve, but like E1 and E2 are multiplied by n. 2. This is finite, of course, surjective and et al. And this map induces the inclusion via pullback. O is the coordinate ring. I'm sorry, via pullback. Okay. Now, the very starting point of the construction is the existence of certain function in the very starting point of the construction. Is the following proposition is, so E is an elliptic curve over scheme S, and choose a prime C, which is the coprime to 6. Then there exists a unique function, unique non-vanishing function, rather than not just function, section, sorry. It's the C theta E lies in here. So OE, but I remove the C torsion. But yeah, it's non-vanishing such that it satisfies the several properties to be uniquely characterized. Its divisor is fixed as follows. on E. And it's invariant under norm map in the following sense. So, and A will be explained a bit after writing the statement. So this map doesn't change anything for all A. A is an integer indeed here. Is co-prime to C where. So I need to explain what NA means. So first, consider the map E removing AC torsion points to E removing C torsion points. This map is defined by multiplication by A. And from here, we have natural map, so O E removing C torsion to OO E removing AC torsion. So this is natural map, and considering the norm map, the corresponding norm map is this NA. So, norm map. This is NA. And under this map, yeah, it is stable. And let me choose another D, which is also co-prime to 6. Then we have the following equality. So d theta E is C squared times C upper star d theta E, and taking inverse equals C theta E d squared d upper star C theta E inverse in O E removing CD torsion and taking the unit, and the C and D's are defined as follows, where of course just everything is just induced from just multiplication map C and D.
Chano, there's a question.
Sorry, there is a missing 2. Sorry, I mean, you mean this? There is
No, I mean in point 1, point II, you have norm of A and then theta CE, which is equal to theta CE. Should it be the same indices?
Yes, yes.
Okay.
Yeah, it doesn't change. Yeah. Okay. And from this natural map, this C upper star is defined by E removing D torsion goes to O E removing CD torsion. And D is also same, defined in the same manner. Okay, so this is the map. Of course, it's very complicated, but like it also has the very explicit way to see this, although still it's complicated. So the third property is it's a complex analytic version. And we can really write down what they are in the following sense. So let me see. Okay, this now tau is the element in the upper plane, and z is a complex number, and removing C inverse z tau plus z. So these are two variables, and I write down C theta tau z is the value of C theta. Now I need to put the elliptic curve here. My elliptic curve is the C quotient by z tau plus z. So this is over C at z. This is the definition. Then we know the explicit form of this value. Then this is the content of this proposition. It's a bit complicated. So Q, the 1/12 times C squared minus 1 and times minus T to the 1/2 C minus C squared times gamma Q of T C squared times gamma Q TC inverse, where, okay, now I need to figure out all these variables here. Q is e to the 2 pi I tau, and T is the 2 pi I z, and gamma Q is as follows. So gamma Q of T is the following infinite product. Times, okay, 1 minus Q to the n times T. And now another infinite product, Q minus 1 minus Q to the n times T inverse. Okay, so yeah, that's the kind of complex analytic incarnation of this C theta E. And the fourth condition is it's a kind of invariance under an isogeny. If I have an isogeny H from E to E prime, isogeny of elliptic curve over S of degree prime to C, then the corresponding null map send C theta E to C theta E prime. Okay, these are the function we start, and about this Kato zeta element, everything will be obtained from this. Okay, and people say like Kato's Euler system come from Ziegel unit, and Ziegel unit will be constructed from this function. So now I define what Ziegel units are. So now CG alpha beta lies into some union of the all yn, and if I remove C, then we allow the denominator. So from here, we will get like a C, D, Z, blah. And from here, we just get the Z something. And this element will be integral, but this one allows the denominator. And I need to figure out what these numbers are. Like C alpha beta is our number. Alpha beta is a pair, lies in the Q mod Z. But like I do not allow both are 0. And C is the coprime to 6 and order of alpha and order of beta. So order alpha means like if n is the order and the minimal integer, which makes n alpha is 0. In the same manner, beta is defined in the similarly. And one good property is from the chosen alpha beta, we can really specify the level. So properties. Now C G alpha beta lies in here. And in the same manner, Z alpha beta also lies in here. So without making any union, if n alpha and n beta are 0. Also, they are also related as follows. Also, CG alpha beta. Sorry, is a CG alpha beta is G alpha beta and is C taking the C square powered times G C alpha C beta, the inverse in this, in here. Okay, these are so-called Ziegel units, and how to produce these elements from the C theta E. See how to produce these elements. And now my E will be an universal elliptic curve. And n is always larger than or equal to 3. And this is universal elliptic curve. And there are sections E1, E2, which form the basis of n torsion of E. Okay, in this setting, I want to construct CG alpha beta. So we choose n satisfying n alpha equal and n beta are 0. N is chosen to satisfy okay. Then we can write alpha beta is A over n and B over n lies in the 1 mod nz quotient z, quotient by z, like this, with A, B's are now integer. Then we define a map iota alpha beta is a map from the modular curve to the universal elliptic curve. AE1 plus BE2. So we have the map. And in fact, the image lies in the here. So we can remove the C torsion because this means like an image of this map it does not meet with a C torsion of elliptic curve. Since we chosen alpha beta satisfies that. So since C is or alpha times or beta is 1, and they are coprime, and the alpha and beta are not both 0. Okay, in this situation, so now we can define the C, G, alpha, beta as follows. So iota alpha beta upper star C theta E is the Ziegler unit. And G alpha beta can be defined as follows. So CG alpha beta tensor C square minus 1 inverse in Q. Of course, we should not make the denominator equals 0. So we take C is first. The C is always coprime to 6, and C is not congruent to 1 modulo n, and C is not plus minus 1, of course. And after making this choice, indeed, this guy is independent of C. And conversely, we can recover on the other side. So CG alpha beta is the G alpha beta to C square in a similar manner. C alpha, C beta inverse for any C satisfying C6N are coprime. Okay, now we have some units, modular units here. Then we want to construct certain elements in the cohomology. Then what we will do is we choose 2 Ziegler units and make a pairing and maps into the second K group of the modular curve. So a little bit K theory. Just state what we need a little bit of K theory. So X is a regular separate Noetherian scheme. Noetherian scheme, then one can define the KIX, so-called the Cullen K group. I only consider the usual K group. And also it admits a cup product. To KIX cross KJX to KI plus JX. And there exists a canonical homomorphism first. Homomorphism, so OX cross to K1. Then combining with this cup product, we have the natural map, so-called the Steinberg symbol. map. So from the pairing of two units to K2. So UV, I just write down, yes, parent, the following notation. Okay, so we will use this pairing later. And I need to introduce group action on modular curve. Group action of GL Z mod NZ on YN. So, okay, GL2 Z mod NZ acts from the left as follows. So let me write sigma. Yes, I just follow the Kato's notation. So Kato used the ACBD. Then E1, E2, the point will be the same elliptic curve, but E1, E2 will become different, where the E1 prime and E2 prime satisfying the following equality. AB, here we use the ABCD usual. And the total, the constant field is the Q zeta n. So sigma zeta n will be zeta n to the determinant of sigma on the constant field. Okay, so we'd like to define the Euler systems in K2 as follows. So two Ziegel units, and we will take a pairing, we get the one element. But like each Ziegel unit, they have their own level. So we will have like we will see some strange level structure. We need two variables for that. So I choose two numbers, mn, then we need another modular curve, ymn. And how do we get this? So first we choose a big number, big level, L larger than or equal to 3, such that M divides L and N divides L. So L is very large. And so we will define this modular curve as the quotient of YL. And it is known that it will be independent of the choice of L. And we need to specify what G is, where G is a subgroup of GL to Z mod LZ. Satisfying the following kind of the congruent subgroup condition, but like we have two parameters. So we will have the two conditions. The upper part, so the ABCD is congruent to modulo M, looks like this, and modulo N looks like this. And we also have the smooth compactification like this. Okay, so the YL quotient by this, then we get YMN, and which is independent of the choice of L. Smooth compactification. And if m plus n is larger than or equal to 5, then this curve also represents a functor. And we will write as follows. So Q scheme to sats. So S maps to also this triple, but it will become more complicated. So E's are same, elliptic curve over S, and E1, E2 are sections. Oh, E over S, such that now we have two parameters, so we should be more careful. So ME1 is 0, and NE2 is 0. And we define the map Z mod MZ times Z mod NZ to E, and A and B maps to AE1 plus BE2 is injective. Okay. That's the optoisomorphism. And the natural map, so if M divide L and N divide L, and N divide L, then there is a natural map YL to YMN as follows. So here I have the following triple, then it goes to the same elliptic curve, but L dividing M times E1 and L dividing N times E2. Okay, this is the what YMN is. Okay, now we can define the element. Okay, Z element. So MN, both are larger than or equal to 2, and I ask their summation is larger than or equal to 5, and I choose CD. Positive integer such that C and 6M are coprime, and D and 6N's are also coprime. Then, so-called the CDZMN is defined as the pairing of the following two Ziegel units, CG 1 over M 0 and DG 0 1 over N. Lies in K2 YMN. And if I remove the all C and D, then we have the similar thing. So Z1 over M0 and G0 1 over N. Then we need to allow the denominator like this. So this is the very starting point. So this is the zeta element, and all the other zeta elements will be like derived from this. And yeah, it satisfies all the expected norm compatibilities, which I will not say in this talk. So all the expected compatibilities. And we can expect the corresponding zeta function. So, but like I defined this zeta elements for the whole modular curve. So my zeta function, not my zeta function, Kato's zeta function, or Beilinson's one, will be like a Hecke operator version of that. So ZMN, the capital Z, S will satisfy the following. I will be defined as follows. So sum runs over N, but like a coprime to M. And the I will not say more detail, but like a Tn is the dual Hecke operator. Times 1 over n 0, 0, 1, and upper step pullback by the action of this matrix times n minus s. S is the complex variable. So it's a kind of infinite sum of the Hecke operator times the n minus s, and this guy acts on the Betti cohomology of y mn complex points and C. And this is also isomorphic. So using Burungale duality, H, the homology of the modular curve. Sorry, here I put X. And so I take the relative homology. So cusps here. And over Z tensor C. And here, there's an element from 0 to I infinity. And it maps to so-called delta Mn. And the theorem of Beilinson is the following. So theorem. So there exists a regulator map. And K2 Y Mn goes to H1 Y Mn complex points. And the coefficient is now put R times I. Then ZMN maps to the following the special values of zeta function. So limit s goes to 0, 1 over s times z m n s times 2 pi I times delta mn. But like I need to put the negative sign here is a complex conjugate x by -1. Anyway, yes, it's something like this. So that's the Beilinson's theorem, and in some sense, like everything starts from also like one can regard everything starts from this theorem. So up to now, we only have the elements in certain Ymn over Q. But in order to have the Euler system, what we want to have is that we want elements in Y1n over a billion extension, right? To have Euler system. So we need to convert from this to this. And so we want to have the Euler systems on x1n over qzm. This is what we want to do. So elements in K2 ymn and elements in K2 of y1n tensor qzm, like this. Okay, so in this process we choose two like parameters in the zeta elements we first seen. So it's Cauchy and S appears here. So there are two types of zeta elements depending on the choice of this Cauchy S. In terms of Cauchy S. The first one is the Cauchy is chosen as the two number A of A. It's just notation. This is just symbol. The content is the A and capital A's are integer, and the capital A is chosen to be positive integer. These are parameter. And S is the prime, which divides the M and A. And the another choice is the Cauchy is chosen to be an element of SL to Z, and S will be both are like a set of primes indeed, like a prime L and L dividing M and the conductor N, the level N. Okay, so the zeta elements from 1 will cover bad Euler factors. So we can deal with bad Euler factors without just removing them. And from 2, we can deal with certain interrelation issues in zeta elements. And the goal is to define so-called the Z1NM Cauchy S, which lies in K2 Y1N tensor Q zeta M tensor Q, because I do not use the C and D. So the first one, okay, what I want to say is that N and M are fixed. So we will choose all the other things depending on this N and M. So choose M larger than or equal to 1, L larger than or equal to 4, such that MA dividing M and N divides L, M divides L, and S is chosen to be L, the prime L, the L dividing M, and L is the L is another set of primes, and L is contained in S or L divided M. Oh, it's complicated. Okay, and since my Cauchy is the small a of capital A, and I consider in the map at the level of the upper plane, tau maps to A inverse times tau plus small a. Then there exists a unique map YML to y1l y1 of n tensor q zeta m with a which is compatible with star. And considering corresponding norm map, yeah, so-called the TMA of A is the K2 YML maps to K2 YN and Y1 of Y1N tensor Q zeta M. But I forgot, yeah, so everything I need to tensor Q because I didn't put C and D. So ZML maps to the element we want. And also this is independent of the choice of ML. Yeah, this is the first one. And the second one is also defined as follows. So we choose L is larger than or equal to 3 such that M divides L and N divides L and S is chosen to be a set of prime dividing L. And there exists a canonical projection from the YL to Y1 of N times Q zeta M and corresponding no map. But we have some twist here. K2YL, okay, tensor Q to K2Y1N tensor Q zeta M tensor Q. So ZLL, but like I take the pullback via my matrix Kusi, and its image will be the zeta elements in this Y1 N over Q zeta M. And of course, it's also independent of choice of L. And there are like of course, with the CD version, then we can remove all the tensor by Q. So we get integral elements. So okay, now we give some summary, what we've done. So everything starts from C theta E, and we construct the Ziegel units. So CG alpha beta. And taking the pairing, we get an element in K2YMN. Okay. And now from here, there's some complicated map to the tau cohomology. So H1, sorry, it's the, yes. Now, because we just working with the YMN, there will be no abelian extension here. So first the tau cohomology, YMN, ZP coefficient, and take the twist by K minus R. And So I need to explain where does it come from, but like so in this process, there are several things are involved. Chan character map to goes to indeed H2, and using the Huxley-Serra spectral sequence, we will get the map from the H1 of H1. And in this process, indeed, like K R primes are involved, and there exists some twist, so-called Sula twist, which we indeed everything is need to be like taking mod p to the n and taking the limit. Such a thing is required, and as I said, Huxley-Serra spectral sequences are required. And from here, one can take like a dual exponential map. Then we will get so-called the zeta modular form. And of course, we can rewrite everything. Yeah, can rewrite everything here with the y1n tensor q zeta m. And this will give us a genuine Euler system. But of course, this is Euler systems over the whole modular curve. So indeed, in order to have the result for one form, then we need to take a quotient of that with respect to the Heck action. So this is the height 1 prime corresponding to a new form in the Heck algebra. Then we need to tensor T modulo, just the PF for all these spaces. Then we will get the result for each modular form. So zeta elements for each modular form. And another direction is indeed, and so where the zeta modular form comes from, indeed, another way to use this C theta E is that we can construct the Eisenstein series. A specific type of Eisenstein series, and taking product of two Eisenstein series, we construct the zeta modular forms, which appeared in here. Yes, they are same. And using the Rankin-Selberg method, and we get a zeta value formula of this zeta elements. So zeta elements. That's the that's the whole picture of this construction of zeta elements. And now I have 30 minutes, and I think the construction is rather too involved and tough. And let me move to another topic about it looks more like interesting.
Shall we take a quick pause for any questions at this
Sure.
moment?
Sure. Okay. Before moving the topic, if you have a question, please let me know.
Any questions from the audience?
Okay.
Yeah.
Can I just move to the next?
Yeah, you can go on. Yeah.
Okay. Now it's a completely different topic. Is about so what I want to say at the end is about a more refined application of the Kato's, or let me say Kuliback system. So I want to put the perspective into this context of Kolyvagin systems more. So, okay. Okay, let me recall the notion of the Kolyvagin primes in the cyclotomic setting. So L is the contains the pk, means L is a good prime, not P, and L is congruent to 1. Of course, the elliptic curve is fixed in my mind. And P is also fixed, modulo P to the K. And AL is congruent to L plus 1 modulo P to the K. And when I say N lies in the mathcal and K is a square free, which means the square free product of these primes in PK. And IL, ZP, is an ideal generated by L minus 1 and 1 minus AL plus L and ZP, which lies in, of course, the PK ZP. And IN ZP means sum of IL ZP, L dividing N. And so what is the complex analytic counterpart of the Kato's Kolyvagin system is as far as I understand this, that's the following number. Define delta n tilde is sum runs over a z mod. Of course, this n is I always chosen to be here. Z mod nz cross and the modular symbol plus part. And I take the mod in reduction times L runs over n, and I consider discrete log, and I already chosen like a primitive root modulo L, and evaluating at A, and taking also modulo in reduction. So which lies in Z mod P modulo in ZP, which I named it Kurihara numbers. In the case of class group, it is also called the higher annihilator. And so why delta and tilde? And first, this makes Kato's Kolyvagin system, I use kappa n, computable. And also appears in the refined Iwasawa theory due to Kurihara. Of course, I need to explain what computable means here. Which means the divisibility of kappa n. In other words, like kappa n lies in p to the something times, yes, Masato Kurihara. P to the some power lies in the Selma group, and p relaxed and n transverse q, but yeah, it's scalar modulo naturally t modulo int. And yeah, so using delta n, then we can like say something on this divisibility. compute this via delta n tilde. So, okay, so one picture is, so Kato's Kohlberg system, and another Kohlberg system, so-called Kohlberg systems of Gaussian type, which are very different indeed. So in the classical case, like this corresponds to the cyclotomic unit Euler system, and this corresponds to the Euler systems of Gaussian type. So if Kato's Kohlberg system is non-zero, then we know the structure of P-Strick-Salma group. Due to Major Rubin. In terms of kappa n. And Kurihara also obtained the structure of the usual Salma groups in this case. In terms of delta n. Due to Kurihara. And yeah, then I'm trying to make the connection. It's in progress. And okay, so maybe I need to show an interesting example why what's the advantage of using this delta n. So it goes more than Birch and Swinnerton-Dyer conjecture in some sense. Of arithmetic applications of delta and tilde. So this example is due to Kurihara in the recent preprint in his webpage. So I choose the following elliptic curve. Y squared plus y is x cubed minus, okay, I will write down the bunch of numbers here. So 170324726259173x minus 270614368527503063009, which is the LMFDB. Its conductor is 423801, and its index is the CI1. Okay, good. Okay, then what do we know is it has rank 0, so its L value doesn't vanish, and we know the value is 10,000. So 2 to the 4 times 5 to the 4. And it's easy to see this comes from Tamagawa number. And this should contribute the Tate-Shafarevich group. So the question is the following. So this elliptic curve, the 5 torsion, certainly has order 5 to the 4. And I know the Tate-Shafarevich group has square order. The direction of the same, how can I say that? Direction of the same abelian group. So we will have this or Z mod 5Z 4. Okay, that's the question. And certainly Birch and Swinnerton-Dyer conjecture will not say anything on this question. because it only concerns the size. And using this, the delta tilde, then what we can compute is the following. So 11 and 41 are the Kolyvagin primes for this elliptic curve with respect to prime 5. So P is 5, sorry. Yeah, P is 5. And this guy is non-zero modulo 5. And the number, the divisor bound the number of generator of Selma groups. In this case, multiple situation. This implies this guy is a Z mod 5Z square. So this 2 comes from the number of the divisors like this. So this removes this case. So this is the correct one. So this implies the T-Sharp-Furbish group is 5-part. It's isomorphic to Z mod 25Z. It's Dressel. So it has more information than the Birch and Swinnerton-Dyer conjecture. And also, this non-vanishing implies the following explicit description of the Selma group for the multiple case. Furthermore, we have an isomorphism. So from the same elliptic curve, the 5 torsions, the Selma group is isomorphic to E, so 11-odic number, so 11-odic, tensor Z mod 5Z, Draxum, E of the Q41 completion, so completion at 41 times Z mod 5Z. So yeah, much kind of a semi-local description of Selma groups. This gives an explicit semi-local, this semi-local description of multiple Selma group. Okay, so then let me introduce some theorems of Kurihara and Sakamoto and my former work, and combining them, we can deduce a version of the Wei-Zhang's, the cyclotomic version of Wei-Zhang's work. Okay, let me write down the theorem of Kurihara in the Iwasawa 2012 proceeding plus the recent preprint. So E over Q is an elliptic curve. Now P is non-anomalous, good ordinary at P, and good ordinary for E, sorry, or the AP is 0, and P does not divide Tamagawa number, and the multiple representation is surjective. Let me just say that E has large image, and cyclotomic mu invariance is 0, and Iwasawa main conjecture holds, and the periodic high pairing is non-degenerate. Then, first result is delta n is non-zero for some n, mod p, for some n lies in the scale-free product of the Kolyvagin primes. Yes, you're right. Second, not just mod p Selma groups, the p infinity Selma groups is completely determined by delta n as a cofinite regenerative GP module. And this use his Kolyvagin systems of Gaussian type. And very recent work of the Sakamoto, he proved the kind of the converse. Oh, not converse, sorry, I proved converse. So what Sakamoto did is he removed the use of the periodic non-degeneracy of periodic high pairing. That's what I wanted to say.
Chano, there's a question from Mahesh in the chat.
Rest type implies the P part. Let me see. Does he assume? Does it implies the P part? I'm not sure. I didn't assume. Yeah, the finiteness of Shah. Yeah. And theorem due to Sakamoto is all similar, but like he removed the use of the non-degeneracy of periodic high pairing, and also he only concerned the good ordinary reduction case in his preprint. Non-anomalous good ordinary for E, and E has large image, and mu equals 0, and P does not divide the Tamagawa number. Then the Iwasawa main conjecture implies that delta n is non-zero modulo P for some n. And proof used the recent theory of the Kolyvagin system of rank 0. Of course, in the usual theory, the Kolyvagin system of core rank 0 is trivial, but he changed a bit. He got a theory of the rank 0 Kolyvagin system. And there exists the converse result. It's done by Myung-il Kim and Haesang Sun and myself for the good reduction case, and also my work with Nakamura about the additive reduction case. Nakamura. So non-anomalous good reduction. So I'm okay with the super singular case or additive reduction. And I also assume the large image. And P does not divide Tamagawa number. Then if delta n is non-zero modulo P for some n, then the Iwasawa main conjecture holds. More precisely, so non-vanishing of delta n implies the non-vanishing of the corresponding Kato's Kolyvagin system, which implies the Iwasawa main conjecture. So this is so-called the primitivity of the Kolyvagin system. And one remark is that I always assume that P does not divide Tamagawa numbers, as the Francesca said in the very first moment in his last lecture. If P divides Tamagawa number, the mod P reduction of Kolyvagin systems are forced to be 0. Remark is that if P divides Tamagawa number, then kappa n is congruent to 0 modulo P for all n. This is observed via Major Rubin and Boyle product. And in the signal point case, I think Dimitar Jetchev also recognized this kind of phenomena. So combining all these three is the following corollary. So E is a good ordinary. P, of course, non-anomalous, sorry. And E has large image. And mu equals 0. And P does not divide the Tamagawa factor. And Iwasawa main conjecture holds. Then it shows the corresponding Kato's Kolyvagin system does not vanish modulo P. So this is the cyclotomic version of Wei Zhang's result. On his Kolyvagin conjecture. And unfortunately, we need to assume the cyclotomic mu equals 0. But in the anti-cyclotomic cases, there are many mu equals 0 are proved. So yeah, it's reasonable to assume this kind of thing here. And yes, and I think let me stop here. Yeah, thank you very much.
So there's a question from Timo on the chat.
Yeah, pretty sure. I think so. My result concerned the gel type of Billiam varieties over Q, and all the other Kurihara's or Sakamoto's results also, yeah, is easily generalized to them. It's just changing all the ZP by the ZP or QP by the completions of Hackett fields. Then yeah, it doesn't. It's not very different, I guess.
Any other questions for Chanho? I don't see many raised hands on the chat. So, okay, if not, let's thank Chanho again for this wonderful course on Kato's Euler Systems.
Yeah, I enjoyed it a lot, and thank you very much for the nice organization. Thank you very much. Yeah.